Today we'll discuss a very important topic in complex numbers, and that is the nth root of unity. Now when we say nth root of unity, we simply mean some number z such that z is equal to 1 to the power 1 by n. We can also write this as z to the power n minus 1 equals 0. So this equation z to the power n minus 1 equals to 0, its degree is n, and any polynomial equation of degree n will have exactly n roots. So this equation will have n roots. So for this equation, z to the power n minus 1 equals 0 or 1 to the power 1 by n, there will be n roots of unity. Sometimes, rather than saying it is nth root of unity or expressing the polynomial in terms of z to the power n minus 1 equals 0, they may give the condition that the roots of this equation 1 plus z square up to z to the power n minus 1 equals 0. Now this is nothing but the GP. We can write this GP as 1 and then z to the power n minus 1 upon z minus 1 equals 0. So from here we'll get this condition that z to the power n minus 1 equals 0, where z is unequal to 1. So this equation also, it will represent the nth root of unity except when the value of z is 1. Now first what we'll do is we'll find these n roots of unity. Now we know that we can express 1 as cos 0 plus iota sin 0, but then this equation, it will have n roots. So what we'll do is, rather than taking this as 0, we'll write this as cos 2 pi r plus iota sin 2 pi r. Now we need 1 to the power 1 by n. We can write this as cos 2 pi r plus iota sin 2 pi r to the power 1 by n. We can write this as e to the power iota 2 pi r by n, where the value of r varies from 0 to n minus 1. So the n roots of unity, they are 1 e to the power iota 2 pi by n, e to the power iota 4 pi by n, e to the power iota 6 pi by n, up to e to the power iota 2 pi n minus 1 divided by n. So these n complex numbers, they are n roots of unity. Now what we generally do is we write this e to the power iota 2 pi by n as some alpha or omega. So if we let e to the power iota 2 pi by n as some alpha or omega, then we say n roots of unity are 1 alpha square up to alpha to the power n minus 1. And if we choose omega, we write them as 1 omega square and omega to the power n minus 1. And here this omega is not cube root of unity. This omega is nth root of unity. Now we'll start writing some results on nth root of unity. And the first result is, let alpha equals e to the power iota 2 pi by n, or we can write this as cos 2 pi by n plus iota sin 2 pi by n, then 1 alpha square and alpha to the power n minus 1 are n roots of unity, and these n roots of unity, they are in geometric progression. So these n roots of unity, they are in GP. Now the second result is, since alpha is nth root of unity, it will satisfy this equation z to the power n minus 1 equals 0. That means alpha to the power n, it will always be 1. So if we have any higher power of alpha, say alpha to the power capital N, what we'll do is we'll express this alpha as sum an plus r, where this r, it can take the value 0, 1, 2 up to n minus 1, and alpha to the power n is 1, so it will be simply equal to alpha to the power r. Say for example, suppose we have 7th root of unity and we have to find alpha to the power 2021. If we divide 2021 with 7, we'll get this as 288 and remainder will be simply 5. So we can write this as simply alpha to the power 5. So if alpha is 7th root of unity, then we can simplify alpha to the power 2021 as alpha to the power 5, and that's our second result. Now here the question is, if omega is 5th root of 2 and x equals omega plus omega square, then prove that x to the power 5 equals 10x square plus 10x plus 6. Now since omega is 5th root of 2, that means omega to the power 5 will be equal to 2. Now we'll use this expression x equals omega plus omega square and we'll take its 5th power. So x to the power 5 will be omega plus omega square to the power 5. Now we'll use binomial expansion. It will be 5c0 omega to the power 5 plus 5c1 omega to the power 4 into omega square plus 5c2 omega cube into omega to the power 4 plus 5c3 omega square into omega to the power 6 plus 5c4 omega into omega to the power 8 plus 5c5 into omega to the power 10. Now we know that omega to the power 5 is 2. We can write x to the power 5 as 2 plus, now this is 5. Now again omega to the power 5 is 2, so it will be into 2 omega, 5c2 is 10, it will be 2 omega square plus 5c3, which is 10 into 2 omega cube plus 5, 2 into omega to the power 4 plus omega 10, which is omega to the power 5 square, and that is 4. So x to the power 5 will be 6 plus 10 omega plus 20 omega square plus 20 omega cube plus 10 omega to the power 4. Now we'll write this as x to the power 5 equals 6, and then we'll take 10 common, omega plus omega square, and then here we'll take omega common, omega plus omega square, and plus 10. Here we'll take omega square common and it'll be omega plus omega square. Now omega plus omega square is nothing but x. So we'll write this as x to the power 5, 6 plus 10 into 1 plus omega plus omega square into x, and again omega plus omega square is x, so we'll get x to the power 5 equals 6 plus 10x plus 10x square. So x to the power 5 is 10x square plus 10x plus 6, and this is what we need to prove. Now third result is, since alpha is e to the power iota theta, then 1 upon alpha will be e to the power minus iota theta. So we can write 1 upon alpha as alpha bar. So if we have any nth root of unity, say alpha, then we know that alpha to the power n equals 1. We can express this alpha as alpha to the power n minus r into alpha to the power r will be equal to 1. We can write alpha to the power n minus r will be 1 upon alpha to the power r, and that should be alpha bar to the power r. Now say for example, alpha is fifth root of unity. Now we know that alpha to the power 5 equals 1. Now we can write alpha to the power 4 equals 1 upon alpha, and alpha to the power 4 will be equal to alpha bar. In the same way we can write alpha cube, it is equal to 1 upon alpha square, it will be simply alpha bar square. So there is a relationship between powers of alpha and powers of its conjugate. Now this fourth result is sum of n roots of unity, which is 1 plus alpha square up to alpha to the power n minus 1, it is 0. So sum of all the roots of unity, it is simply 0. We can also write this sum as this summation r varies from 0 to n minus 1 e to the power iota 2 pi r by n, or we express it as this summation r varies from 0 to n minus 1 cos 2 pi r by n plus iota sine 2 pi r by n, and it will be equal to 0. That is, sum of all the n roots of unity is simply 0. Now this summation, it starts from 0. At times we'll get questions where this sum will start from 1. They'll say r varies from 1 to n minus 1 e to the power iota 2 pi r by n, or this summation r varies from 1 to n minus 1 cos 2 pi r by n plus iota sine 2 pi r by n. Now when we start the summation from 1, that means we are talking about alpha plus alpha square up to alpha to the power n minus 1. So we'll take this 1 on the right hand side, then this sum will be nothing but minus 1. So this summation will now be minus 1. Now there are two corollaries to this result 4, and the first one is, if we take conjugate of this sum, then we can write 1 plus alpha bar square up to alpha bar to the power n minus 1 will also be 0. So sum of conjugates of all the roots is also 0. That is, this summation r varies from 0 to n minus 1 cos 2 pi r by n minus iota sine 2 pi r by n will also be 0. And the second corollary is, if we multiply it with alpha to the power r, we can write alpha to the power r plus alpha to the power r plus 1 plus alpha to the power r plus 2 up to alpha to the power n minus 1 plus r will also be 0. That is, sum of any n consecutive powers of alpha, it will also be 0. Now say for example, Suppose alpha is 7th root of unity. And we need to find alpha plus alpha square up to alpha to the power 22. Now altogether there are 22 powers in this sum. Now we know that sum of any 7 consecutive powers will be simply 0. So we can express this as alpha plus, and then we'll have 3 sets of consecutive powers of alpha having 7 consecutive powers. So this sum will be 0, this sum will also be 0, this sum will also be 0. So this expression will simplify to simply alpha. Now here the question is, we need to find the value of this summation, which is summation k varies from 1 to 6 sine 2 pi k by 7 minus iota cos 2k pi by 7. Now we know that it is somehow related to 7th root of unity because we have 2 pi by 7 here, and then this k, it varies from 1 to n minus 1, which is 6. But it is not cos theta plus iota sin theta. It is sin theta minus iota cos theta. Now what we'll do is, we'll assume there is this 1 here and 1 is iota to the power 4. So if we take minus iota common, then we can write minus iota, and then this summation k varies from 1 to 6 cos 2k pi by 7 plus iota sine 2k pi by 7. Now this summation where k varies from 1 to n minus 1, cos 2 pi k by n plus iota sine 2k pi by n is nothing but minus 1. So this value, it is minus 1. So value of this summation will be simply iota, and that's your option D. Now here the question is, if omega is nth root of unity, then we need to find this summation, which is summation r varies from 1 to n ar plus b omega to the power r minus 1. Now we can write this summation as this sum as, and we can split this as summation r varies from 1 to n ar into omega to the power r minus 1, and then plus b into this summation r varies from 1 to n omega to the power r minus 1. Now sum of any n consecutive powers of omega, it is 0. So this second expression will be simply 0. We can write this sum as a into, now this is 1 plus 2 omega plus 3 omega square up to n into omega to the power n minus 1. Now what we'll do is, we'll write this series again by displacing one term and then multiplying it with omega. So we can write this as a, and here will be omega plus 2 omega square n minus 1 omega to the power n minus 1, and then plus n into omega to the power n. Now omega to the power n is nothing but 1. So this is 1, and if we subtract second series from first, we can write 1 minus omega into s, and here will be a, and then it will be 1 plus omega square up to omega to the power n minus 1, and then minus n. Now sum of n consecutive powers of omega will be simply 0. So we can write this sum as minus na upon 1 minus omega, or na upon omega minus 1, which is your option C. Now another important result is, suppose roots of unity are 1 alpha, alpha square, and alpha to the power n minus 1, and r is some number which is not a multiple of n. Then sum of rth power of these roots, that is 1 to the power r plus alpha to the power r, alpha square to the power r plus alpha n minus 1 into r will also be 0 if r is a multiple of n. Then in that case alpha to the power r will be simply 1. So this series 1 to the power r plus alpha to the power r, alpha to the power 2r plus alpha to the power n minus 1r will be 1 plus 1 plus 1 plus 1 n times. Then this value will be simply n. We can prove this result using GP. Now this is nothing but a GP. Sum of this GP will be a, which is 1 to the power r into r to the power n. So it will be alpha to the power r to the power n minus 1 upon alpha to the power r minus 1. We can write this as alpha to the power n to the power r minus 1 upon alpha r minus 1, and alpha to the power n is 1. So this sum will be 0 for any power where this power is not a multiple of n, and if the power is a multiple of n, then in that case this sum will be equal to n. Now say for example, suppose 1 omega square and omega to the power 6r, 7 roots of unity, then 1 to the power 2021, omega to the power 2021, omega square to the power 2021 up to omega 6 to the power 2021 will be 0. And if we have a multiple of 7, say for example 1 to the power 21 plus omega to the power 21, omega square to the power 21 up to omega 6 to the power 21. Now this is 1. Now omega to the power 7 is 1. So it will be 1 plus 1 plus 1 7 times. Then this sum will be simply 7. So if r is not a multiple of n, then sum of rth power of all the roots will be simply 0. And if r is a multiple of n, then this sum will be simply n. Now here the question is, find the sum of all 1000 power of 17th root of unity. So we just need to find sum of all 1000 power of 17th root of unity, where this r, it varies from 1 to 16. Now 17, it doesn't divide 1000. That means sum of this series is simply 0. Now the sixth result is product of all the roots of unity, which is 1 alpha square up to alpha to the power n minus 1. It is minus 1 to the power n minus 1. Now we can verify this. Now here sum of powers will be alpha to the power n minus 1 by 2. Now alpha is e to the power iota 2 pi by n. So we can write this as e to the power iota 2 pi by n into n minus 1 by 2. This 2 will cancel, n will also cancel. We'll get this as e to the power iota n minus 1, which is cos n minus 1 pi plus iota sine n minus 1 pi. Now sine n pi will be 0. So this product will be equal to cos n minus 1 pi. Now if n is odd, say for example n is suppose 3, then we'll get this as cos 2 pi, which is 1. And if n is even, we'll get this as cos pi, which is minus 1. So we can write this result as minus 1 to the power n minus 1. So product of all the nth root of unity, it is minus 1 to the power n minus 1. Now this seventh result is, suppose 1 e to the power iota 2 pi by n e to the power iota 4 pi by n e to the power iota 6 pi by n up to e to the power iota 2 pi n minus 1 to the power n are nth root of unity, then for each of these roots their modulus is 1. That means all these roots, they lie on a unit circle with center at origin. And if we write argument of these roots, then argument of 1 is 0. Here the argument is 2 pi by n. Here it is 4 pi by n, 6 pi by n up to 2 pi n minus 1 divided by n. Now between any two roots there is an angle 2 pi by n. From here we can say nth roots of unity they divide unit circle in n equal parts. So we have this unit circle and then this is 1 and all the other roots, they'll divide this circle in n equal parts. So this is 1, this is alpha square, alpha cube, this is alpha to the power n minus 1, alpha to the power n minus 2. And here this angle is 2 pi by n. This is also 2 pi by n. This angle is also 2 pi by n. So angle between any two consecutive roots is 2 pi by n. So nth roots of unity, they divide unit circle in n equal parts. Suppose we have cube root of unity. So cube root of unity, they'll divide this unit circle in 3 equal parts. Now one of the root is 1. Now 2 pi by n is 2 pi by 3. So these 3 roots, they'll divide this unit circle in 3 equal parts. Now this is 2 pi by 3. This angle is also 2 pi by 3 and this is also 2 pi by 3. This is 1 omega n omega square. So nth roots of unity, they divide unit circle in n equal parts, and it brings us to our corollary, and which is angle between any two roots of unity, it must be an integral multiple of 2 pi by n. That is argument of sum zi upon zj, it must be equal to 2 pi by n into k, where k is an integer. Now say for example, the question is, let z1 and z2 be nth roots of unity which subtend a right angle at the origin, then n must be of the form where k is an integer. Now if z1 and z2 are nth roots of unity, then angle between z1 and z2, it is given by argument of z1 upon z2, and angle between any two nth roots of unity is given by 2 pi by n into k, where k is an integer. Now it is given that this angle is a right angle, that is, it is pi by 2. And we'll cancel this pi with pi. That means this n, it must be of the form 4k and that's your option D. So angle between two roots of unity can only be a right angle if n is a multiple of 4. Now this eighth result is, suppose 1 alpha, alpha square and alpha to the power n minus 1, they are nth roots of unity. Then we know that they are roots of the equation z to the power n minus 1 equals 0. Now we can also write this polynomial equation in terms of product of linear factors. We can write z to the power n minus 1 as z minus 1 into z minus alpha square and z minus alpha to the power n minus 1 equals 0. So from here we'll get this identity that z to the power n minus 1 will be equal to z minus 1 z minus alpha square up to z minus alpha to the power n minus 1. We'll be using this identity to find some results in terms of product. Say for example, we need to find the value of 2 minus alpha square up to 2 minus alpha to the power n minus 1. So what we'll do is, we'll simply take z as 2, we'll write 2 to the power n minus 1 will be equal to 2 minus 1 is 1, and then it is 2 minus alpha square and 2 minus alpha to the power n minus 1. So value of this product is nothing but 2 to the power n minus 1. Another question which is generally asked in this is to find the value of 1 minus alpha square and then 1 minus alpha to the power n minus 1. Now here we cannot put z as 1 because here left hand side will be 0 and right hand side will also be 0. So we'll end up getting a trivial result. So in that case what we'll do is, we'll write z minus alpha square z minus alpha to the power n minus 1 as z to the power n minus 1 upon z minus 1, and then we'll take this limit z tends to 1. Now we take this limit, we'll get 1 minus alpha square 1 minus alpha to the power n minus 1, and here value of this limit will be simply n. So we'll also be using this identity while solving the problems. Now a corollary to this result is, we know that we can write z to the power n minus 1 as z minus 1 z minus alpha square z minus alpha to the power n minus 1. Now we also know that alpha to the power n is 1 and that alpha to the power n minus 1 will be equal to 1 upon alpha, and which is nothing but alpha bar. So we can write alpha to the power n minus 1 as alpha bar, and what we'll do is, we'll take these two factors together. We can write this as z minus 1 z minus alpha bar z minus alpha square, etc. Now we multiply them, we'll get z minus 1 z square minus alpha plus alpha bar z plus alpha into alpha bar. Now we know that alpha is e to the power iota 2 pi by n, and alpha plus alpha bar will be 2 cos 2 pi by n. We can write this as z minus 1 into z square minus 2 cos 2 pi by n into z plus alpha into alpha bar is mod of alpha square, and modulus of any nth root of unity is nothing but 1. So we have expressed this z to the power n minus 1 as product of linear and quadratic factors. In the same way, we can do it for z minus alpha square also. That one will be z square minus 2 cos 4 pi by n z plus 1. So we'll also be using this corollary while solving the problems. Now the ninth result is if 1 alpha square alpha to the power n minus 1 are nth roots of unity and 1 omega square up to omega to the power m minus 1 are nth roots of unity, then we need to find number of common roots. Now we know that 1 alpha square up to alpha to the power n minus 1, they are roots of z to the power n minus 1 equals 0, and then 1 omega square omega to the power m minus 1, they are roots of z to the power m minus 1 equals 0. Now number of common roots, it is given by this equation z to the power d minus 1 equals 0, where this d is GCD of m and n. Now here the question is, two regular polygons are inscribed in the same circle. The first has 1371 sides and the second has 4039 sides. If the two polygons have at least one vertex in common, then how many vertices in total will coincide? Now we know that any regular polygon can be inscribed in a circle. Now if we assume radius of this circle as 1, then all the vertices of this polygon, they'll coincide with nth roots of 1731. So vertices of this first polygon, they are given by roots of z to the power 1731 minus 1 equals 0. Now for this second polygon, the vertices are given by roots of the equation z to the power 4039 minus 1 equals 0, and they have at least one vertex in common. So this common vertex is 1. Now we need to find how many vertices in total will coincide. Now we know that number of common roots of z to the power n minus 1 and z to the power m minus 1 equals 0 is given by z to the power d minus 1 equals 0, where d is GCD of n and m. So first what we'll do is we'll find GCD of 1731 and 4039. Its GCD is 577. So total number of vertices that will be common, or the vertices in total that will coincide, is 577. Now the 10th result that we use in nth root of unity is related to equations of the form z plus 1 to the power n plus or minus z to the power n. Now we can rewrite this as z plus 1 upon z will be equal to 1 to the power 1 by n, which is nth root of unity, which we can write as e to the power iota 2 pi r by n So we'll write 1 plus 1 upon z, it is equal to e to the power iota 2 pi r by n, and since this equation will have n real roots, we'll say this root is suppose zr. Now we can write zr as 1 upon e to the power iota 2 pi r by n minus 1. Now what we'll do is we'll divide numerator and denominator with e to the power iota pi r by n. Then we can write zr as e to the power minus iota pi r by n upon e to the power iota pi r by n minus e to the power minus iota pi r by n. And the numerator we'll have cos pi r by n minus iota sine pi r by n upon, and in the denominator it is cos theta plus iota sine theta minus cos theta minus minus plus iota sine theta. So it will be 2 iota sine pi r by n. We can write this zr as minus 1 by 2 and then minus 1 by 2 iota cot pi r by n. Now real part of zr is minus 1 by 2, which is independent of r. That means all the roots of this equation will lie on this line, which is x equals minus 1 by 2. So we generally use this result while solving problems. So there will be problems related to z plus 1 to the power n equals plus or minus z. Now here the question is, if 1, z1, z2 and z10 are 11th roots of unity, then match the entries in column A with entries in column B. Now we know that there are 11th roots of unity. Then we can write z to the power 11 minus 1 as z minus 1, z minus z1, z minus z2 and z minus z10. Now we'll divide everything with z minus 1. We can write z minus z1, z minus z2, z minus z10. It is z to the power 11 minus 1 upon z minus 1, and we'll take this limit z tends to 1 both sides. Now on the left hand side we'll have 1 minus z1, 1 minus z2, 1 minus z10, and this is limit x tends to a, x to the power n minus a to the power n upon x minus a. So it will be n a n minus 1, which is nothing but 11. So this a, it matches with 4. Now rather than taking z as plus 1, if we take z as minus 1, on the left hand side we'll get this as minus 2. Here also it will be minus 2, and then minus 1 minus z1, minus 1 minus z2, and then minus 1 minus z10. Now this minus 2 and minus 2 will cancel, and here we have 10 factors. If we take minus 1 common from each factor, we'll get 1 plus z1 into 1 plus z2, 1 plus z10, and it'll be nothing but 1. So this C, it matches with 1. So C matches with 1. Now we look at D. D is nothing but product of all the roots. 1 into z1 into z2 into z10 will be minus 1 to the power n minus 1, which is 11 minus 1, which again is 1. So this D, it again matches with 1. So D, it matches with 1. Now what about option B? Now we know that sum of any powers of all the roots is 0 if the power is not a multiple of n, and it'll be n if power is multiple of n. Now 11 doesn't divide 100, so it simply means that 1 to the power 100 plus z1 to the power 100 up to z10 to the power 100 will be nothing but 0. So this B, it matches with 3. So B, it matches with 3. Now here the question is, how many pairs of real numbers A and B does this relation a plus b iota to the power 2020 equals a minus b iota? Now we'll let a plus b iota as z. We can write z to the power 2020 equals z bar. Now from here we'll get this condition that either mod of z is 0 or mod of z is 1. Now if mod of z is 0, we'll get one solution, and that is value of z is 0. Now we take this first case when mod of z is 0, we'll get the only solution, which is z equals 0. And if we consider the second case that mod of z equals 1, so what we'll do is we'll multiply z both sides. We'll write z to the power 2021 equals 1, that is z is 1 to the power 1 upon 2021, which is 2021th power of unity. So this equation will have 2021 roots. So total number of roots will be 2021 plus 1, that is 2022. So there will be 2022 real numbers A and B which satisfy this relation. Now here the question is, if alpha is non-real and it is fifth root of unity, we need to find the value of 2 to the power mod of 1 plus alpha square plus alpha to the power minus 2 and minus alpha to the power minus 1. Now we know that alpha to the power 5, it is 1. Then alpha to the power minus 2, it is nothing but alpha cube, and alpha to the power minus 1, it is nothing but alpha to the power 4. So we can write this as 2 to the power mod of 1 plus alpha square plus alpha cube minus alpha to the power 4. Now we'll add alpha to the power 4 and we'll subtract alpha to the power 4. Now sum of all fifth root of unity is 0. So this is 0 and we'll get this as 2 to the power mod of minus 2 alpha to the power 4. Now it will be 2 square upon mod alpha to the power 4, and mod of alpha is 1. So it will be 2 square, which is simply 4, and that's your option A. Now here the question is, if x1, x2 and x3 are the roots of x to the power 4 minus 1 and omega is cube root of unity, then we need to find this value. Now we know that we can write x to the power 4 minus 1 as x minus 1 into x minus x1, x minus x2 into x minus x3. Now if we put x as omega square, it will be omega to the power 8 minus 1, and it will be equal to omega square minus 1 into omega square minus x1, omega square minus x2 and omega square minus x3. Now omega to the power 8 is nothing but omega square, so it will cancel. From here we can write omega square minus x1 into omega square minus x2 into omega square minus x3, it is 1. Now for the denominator, we'll put x as omega. So we'll get this as omega to the power 4, which again is omega. So it will be omega minus 1 equals omega minus 1, omega minus x1, omega minus x2 and omega minus x3. Now it'll cancel. So from here we'll get omega minus x1 into omega minus x2 into omega minus x3 will be equal to 1. Now we divide first with second, we'll get this result as 1. Now here the question is, if ZR are the roots of the equation Z to the power 2m plus Z to the power 2m minus 1, Z to the power 2m minus 2 up to plus Z plus 1, then prove that this summation R varies from 1 to 2n 1 upon ZR minus 1 is equal to minus m. Now we can write this equation as Z to the power 2m plus Z to the power 2m minus 1 up to Z plus 1, and it will be equal to Z minus Z1, Z minus Z2 up to Z minus Z2m. Now if we take log both sides, we can write log and then summation Z to the power R, where R varies from 0 to 2m, will be equal to this summation log Z minus ZR, where R varies from 1 to 2m. Now what we'll do is we'll differentiate both sides. We'll get 1 upon this summation R varies from 0 to 2m Z to the power R, and then this summation R varies from 0 to 2m R into Z to the power R minus 1, and on the right hand side we'll get this as this summation R varies from 1 to 2m 1 upon Z minus ZR. Now what we need is ZR minus 1. So what we'll do is we'll put Z as 1. Now if we put Z as 1, we'll get this as this summation 1, and summation 1 will be 2m plus 1 into, now this is summation R, and summation R is n plus 1 by 2, and will be this summation R varies from 1 to 2m 1 upon Z minus ZR. Now this 2m plus 1 will cancel, this 2 will also cancel. Now we'll take this minus common from the right hand side and we'll take it on the left hand side. So we can write this summation R varies from 1 to 2m 1 upon ZR minus 1. Here this Z, it should be 1. It will be equal to minus m, and which is what we need to prove. Now here the question is, if omega to the power j are the nth roots of unity, then show that this summation j varies from 0 to n minus 1 mod of z1 plus omega to the power j z2 square, it is equal to n into mod of z1 square plus mod of z2 square. Now we know that mod of z square is z into z bar. So we can write this as this summation j varies from 0 to n minus 1. This is z1 plus omega to the power j z2, and then it will be z1 bar plus omega bar to the power j into z2 bar. Now omega bar to the power j is nothing but omega to the power n minus j. So we can write this summation as this summation j varies from 0 to n minus 1 z1 plus omega to the power j z2 and z1 bar plus omega to the power n minus j into z2 bar. Now we'll multiply them. If we multiply them, we'll get this as this summation j varies from 0 to n minus 1, and then z1 into z1 bar will be mod of z1 square plus, now here we'll get omega to the power n minus j z1 into z2 bar plus omega to the power j z2 into z1 bar and then plus omega to the power n into mod of z2 square. Now omega to the power n, it is 1. So we can write this summation as summation j varies from 0 to n minus 1, and we'll take them together. It will be mod of z1 square plus mod of z2 square plus z1 z2 bar, and then this summation omega to the power n minus j, where j varies from 0 to n minus 1, plus z2 z1 bar, j varies from 0 to n minus 1, omega to the power j. Now we know that sum of any consecutive n powers of omega is 0. So this is 0 and this sum is also 0, and this is a constant term. So this summation will be n times mod of z1 square plus mod of z2 square, and which is what we need to prove. Now here the question is, let z be a root of x to the power 5 minus 1 equals 0. That means z is fifth root of unity and z is unequal to 1. Now we need to find the value of z to the power 15 plus z to the power 16 up to z to the power 50. Now we know that sum of any n consecutive powers of roots is equal to 0. That means sum of any 5 consecutive powers of z will be nothing but 0. So if we look at these numbers, they start from 15 and they go all the way up to 50. So we'll have z to the power 15 and then plus this first set of consecutive powers from 16 to 20, then from 21 to 25, and finally from 46 to 50. Now sum of all these sets is nothing but 0. So this sum will be nothing but z to the power 15. Now since z to the power 5 is 1, z to the power 15 will also be 1. So value of this summation is nothing but 1, and that's your option A. Now example 30 is, we need to find roots of this equation. Now we are given this equation, which is z plus 1 to the power 5 and it is equal to z minus 1 to the power 5. Now we can write this as z plus 1 upon z minus 1, and this is fifth root of unity, and it is nothing but e to the power iota 2 pi r by 5. Now we'll use componendo and dividendo. So we'll get z upon 1 as 1 plus e to the power iota 2 pi r by 5 upon e to the power iota 2 pi r by 5 minus 1. Now what we'll do is, on the right hand side, we'll divide numerator and denominator with e to the power iota pi r by 5. So we'll get this z as e to the power minus iota pi r by 5 plus e to the power iota pi r by 5 upon e to the power iota pi r by 5 and minus e to the power minus iota pi r by 5. Now this numerator is nothing but, this is 2 cos pi r by 5 upon, and this is 2 iota sine pi r by 5. So this zr, it will be minus iota cot pi r by 5. Now if we put r as 1, we'll get z1, which is minus iota cot pi by 5. Now we put z as 2, we'll get minus iota cot 2 pi by 5. Z3 is minus iota cot 3 pi by 5, and 3 pi by 5 is pi minus 2 pi by 5. So it will be plus cot 2 pi by 5. In the same way, we can write Z4 as plus iota cot pi by 5. So the roots are plus minus iota cot pi by 5 and plus minus iota cot 2 pi by 5, which is your option B. Now it says if W is e to the power iota pi by 11, we need to find this product. K varies from 0 to 11, omega to the power k minus 2 omega to the power minus k. Now we can write this as omega to the power minus k into omega to the power 2k minus 2, where this product, it varies from 0 to 11. Now we'll split it in two parts. So this product, k varies from 0 to 11 omega to the power minus k into this product, k varies from 0 to 11 e to the power iota 2 pi k by 11 minus 2. Now this first one, it is nothing but omega and then minus. This is sum of first 11 natural numbers. So it will be 11 into 12 upon 2, and here it will be k varies from 0 to 11, and this is 11th root of unity. So it will be alpha to the power k minus 2. Now we can write this as omega square to the power minus 11, and here we can write this as 1 into 2 minus alpha square, 2 minus alpha to the power 10, and 2 minus alpha to the power 11. Now omega square is alpha, and alpha is 11th root of unity. So alpha to the power 11 is 1. So this value is 1. This value is also 1. So we'll get this series as 2 minus alpha into 2 minus alpha square up to 2 minus alpha to the power 10. Now we know that if alpha is 11th root of unity, we can write z to the power 11 minus 1 as z minus 1, z minus alpha square, z minus alpha to the power 10. If we put z as 2, we can write 2 minus alpha up to 2 minus alpha to the power 10 will be 2 to the power of 11 minus 1. So value of this product, it will be 2 to the power of 11 minus 1, which is 2048 minus 1, and it is 2047. Now here the question is, if beta n equals to 1 is any nth root of unity, then we need to find this sum. So this sum is 1 plus 3 beta plus 5 beta square. It continues up to 2n minus 1 beta to the power n minus 1. Now we'll write the series again, displacing it by one term and multiplying it with beta. So we'll get this as beta plus 3 beta square, and this is 2n minus 3 beta to the power n minus 1 and plus 2n minus 1 into beta to the power n, and we know that beta to the power n is 1. Now we'll subtract second form first. We can write 1 minus beta s will be 1 plus 2 into beta plus beta square up to beta to the power n minus 1, and here it will be minus 2n minus 1. Now we know that sum of this series is minus 1. So it will be 1 minus beta s and then minus 1 minus 2n plus 1. So sum of this series is minus 2n upon 1 minus beta, and that's your option 2. Now the next question is, let zk equals cos 2k pi by 10 plus iota sine 2k pi by 10. That means zk is 10th root of unity. Now in this column 1, P is for each zk there exists a zj such that zk into zj equals 1. Now if we write zk into zj, zk is e to the power iota 2k pi by 10 and zj will be e to the power iota 2j pi by 10, and if we add them, we'll get iota and then 2 by 10 into k plus j pi, which is e to the power iota k plus j by 5 into pi. Now this result will be 1 if k plus j it is equal to 10. So for any value of k, we'll always get a j such that zk into zj is 1. That means p is true. So this p, it matches with 1. Now q, it says there exists a k such that z1 into z is equal to zk has no solution z in the set of complex numbers. Now we can write this z as zk upon z1. Now zk is e to the power iota 2 pi k by 10 upon e to the power iota 2 pi by 10, which is e to the power iota 2 pi by 10 into a minus 1. So if we choose any value of k from 1 to 9, we'll always end up getting this complex number z. That means this condition that it has no solution is false. So this q, it matches with second. Now we'll come to this r, and which is mod of 1 minus z1 1 minus z2 into 1 minus z9. Now we know that z minus z1 into z minus z2 into z minus z9 will be equal to z to the power 10 minus 1 upon z minus 1. And if we take mod both sides, and if we take this limit z tends to 1, then we'll get mod of 1 minus z1 into mod of 1 minus z2 into mod of 1 minus z9 will be equal to 10. Now if we take this 10 on the left hand side, we'll get mod of 1 minus z1 to mod of 1 minus z9 by 10. It is equal to 1. That means this r, it matches with 3. And for this fourth one, we need to find 1 minus this summation. K varies from 1 to 9 cos 2k pi by 10. Now we know that summation k varies from 1 to n minus 1 cos 2k pi by 10 plus iota sine 2k pi by 10. This value is minus 1. Now comparing real and imaginary part. So from this real part we'll get this summation k varies from 1 to 9 cos 2k pi by 10, and this summation is equal to minus 1. So if we put the value of this summation here, we'll get this result as 1 minus minus 1, which is nothing but 2. That means this S, it matches with 4. So answer to this question is P matches with 1, Q with 2, R with 3, and S with 4. Now here the question is, show that this summation P varies from 1 to 32, 3P plus 2 into this summation Q varies from 1 to 10 sine 2Q pi by 11 minus iota cos 2Q pi by 11 whole to the power 4 pi is equal to 1648. Now from this what we'll do is we'll take minus iota common. We can write this as this summation P varies from 1 to 32, 3P plus 2, and here we'll get this as minus iota, and then this summation Q varies from 1 to 10 cos 2Q pi upon 11 plus iota sine 2Q pi upon 11 whole to the power 4 pi. Now this is 11th root of unity, and we need to find the value of alpha plus alpha square up to alpha to the power n minus 1, and we know that this value is minus 1. So we get this summation as P varies from 1 to 32, 3P plus 2 into iota to the power 4 pi. Now iota to the power 4 is 1, so it will be simply this summation P varies from 1 to 32, 3P plus 2. Now this summation is nothing but an AP. So we just need to find sum of AP. So it will be n by 2. So it will be 32 by 2 into A plus L. Now A is when the value of P is 1. So if we put P as 1, we'll get this as 5 plus, and then L is when the value of P is 32. So it will be 32 into 3 plus 2, which is 98. So it will be simply 16 into 103, which is nothing but 1648, which is what we need to prove. Now here the question is, we need to find this sum Z equals this summation M varies from 1 to 4n plus 1, and then this summation R varies from 1 to m minus 1 e to the power iota 2 pi r by m plus pi by 2 whole to the power m. Now we'll split it in two parts, and we know that e to the power iota pi by 2 is simply iota. So we can write this as this summation m varies from 1 to 4m plus 1, and then it will be iota into this summation r varies from 1 to m minus 1 e to the power iota 2 pi r by m whole to the power m. Now we know that this is nothing but sum of m roots of unity except 1, and this sum is nothing but minus 1. So we'll get this summation as summation m varies from 1 to 4m plus 1, and it will be minus iota to the power m. Now we know that sum of any 4 consecutive powers of iota is 0, and we have 4m plus 1 numbers in the series. So sum of all 4m numbers will be 0. Then we are left with this one number, and this one number will be simply minus iota. So the value of z is minus iota. So this sum is minus iota. It is independent of n, and its real part is 0. So answer to this question is option A and B. Now here the question is, we need to find this summation, which is this sum r varies from 1 to n minus 1 n minus r cos 2 pi by n into r. Now if we reverse the series, we can write this series as this summation r varies from 1 to n minus 1, and we'll replace n minus r with r. So it'll be simply r and then cos 2 pi by n into n minus r, which is summation r varies from 1 to n minus 1. Now here we'll get this as r and this is cos 2 pi minus theta, which is cos theta. So r cos 2 pi r by n. Now we'll add them both. Now if we add them both, we can write 2s as this summation r varies from 1 to n minus 1. Now this r and r will cancel, n into cos 2 pi r by n, or s is n by 2 into this summation r varies from 1 to n minus 1 cos 2 pi r by n. Now we know that for nth root of unity, the value of this summation r varies from 1 to n minus 1 cos 2 pi r by n plus iota sine 2 pi r by n is equal to minus 1. And if we compare its real part, then we know that value of this summation is minus 1. That means this sum, it is equal to minus n by 2, and that's your option D. Now here the question is, solve the equation z to the power 10 minus 1 equals 0 and deduce that sine 5 theta equals 5 sine theta into 1 minus sine square theta upon sine square pi by 5 into 1 minus sine square theta upon sine square 2 pi by 5. Now this is 10th root of unity, and suppose roots are 1 alpha, alpha square, alpha cube, alpha to the power 4, alpha to the power 5, 6, 7, 8 and 9. Now we know that we can write alpha to the power 9 as alpha bar, alpha to the power 8 as alpha bar square, alpha to the power 7 as alpha bar cube, and alpha to the power 6 as alpha bar 4. Now alpha is e to the power I 2 pi by 10, then alpha to the power 5 will be e to the power iota pi, which is nothing but minus 1. So we can write this z to the power 10 minus 1 as z minus 1, z minus alpha square, z minus alpha cube, z minus alpha to the power 4, and z minus alpha 5, which is z plus 1, and then z minus alpha bar to the power 4, z minus alpha bar cube, z minus alpha bar square into z minus alpha bar. Now we'll take z plus 1 and z minus 1 together. We can write this as z square minus 1. We'll take these two together. We'll write z square minus alpha plus alpha bar z plus 1. Next one will be z square minus alpha square plus alpha bar square into z plus 1. Then z square minus alpha cube plus alpha bar cube z plus 1. And finally z square minus alpha to the power 4 plus alpha bar to the power 4 z plus 1. Now alpha plus alpha bar is 2 cos 2 pi by 10. This one is 2 cos 4 pi by 10. This is 2 cos 6 pi by 10, and this one is 2 cos 8 pi by 10. So we'll write this z to the power 10 minus 1 is z square minus 1, z square minus 2 cos pi by 5 z plus 1, z square minus 2 cos 2 pi by 5 z plus 1 z square minus 2 cos 3 pi by 5 z plus 1 and then z square minus 2 cos 4 pi by 5 z plus 1. Now what we'll do is we'll divide left hand side and right hand side with z to the power 5. So we can write z to the power 5 minus 1 upon z to the power 5 will be equal to z minus 1 upon z. We can write this as z plus 1 upon z minus 2 cos pi by 5 z plus 1 upon z minus 2 cos 2 pi by 5. The next one is z plus 1 upon z minus 2 cos 3 pi by 5, and this is z plus 1 upon z minus 2 cos 4 pi by 5. Now we'll let z as cos theta plus iota sin theta. We can write this as 2 iota sin 5 theta will be equal to 2 iota sin theta into 2 cos theta minus 2 cos pi by 5, 2 cos theta minus 2 cos 2 pi by 5, 2 cos theta minus, now cos 3 pi minus theta is minus cos 2 pi by 5. So it will be plus 2 cos 2 pi by 5, and this one will be 2 cos theta and then plus 2, and then cos 4 pi by 5 is minus cos pi by 5 will be plus 2 cos pi by 5. Now here 2 iota will cancel. We'll take 2 common from all the 4 brackets. We can write sin 5 theta equals 16 sin theta, and here we'll take these two terms together. We'll write cos square theta minus cos square pi by 5, and the next one will be cos square theta minus cos square 2 pi by 5. Now we can change cos square a minus cos square b as sin square b minus sin square a. So we'll write this as sin 5 theta will be 16 sin theta sin square pi by 5 minus sin square theta, and then sin square 2 pi by 5 minus sin square theta. Now we'll take sin square pi by 5 and sin square 2 pi by 5 common. We can write this as sin 5 theta equals 16 sin theta into sin pi by 5 into sin 2 pi by 5 whole square, and here will be 1 minus sin square theta upon sin square pi by 5, and the next one is 1 minus sin square theta upon sin square 2 pi by 5. Now this is sin 5 theta and will be 16 sin theta. Now this is sin 36, and sin 36 is under root of 10 minus 2 root 5 by 4, and this is sin 72, and sin 72 is cos 18, and cos 18 is under root 10 plus 2 root 5 by 4 whole square, and this is 1 minus sin square theta upon sine square pi by 5 into 1 minus sine square theta upon sine square 2 pi by 5. Now we'll simplify this. We'll write this as a plus b into a minus b will be 100 minus 4 into 5, which is 20 upon 16 into 16, which is 5 by 16. So now we can write this sine 5 theta is 16 sine theta into 5 by 16 1 minus sine square theta upon sine square pi by 5 into 1 minus sine square theta upon sine square 2 pi by 5. Now the 16 and 16 will cancel. So we'll get this result as sine 5 theta equals 5 sine theta and 1 minus sine square theta upon sine square pi by 5 into 1 minus sine square theta upon sine square 2 pi by 5. And this is what we need to prove. 5 sine theta 1 minus sine square theta upon sine square pi by 5 into 1 minus sine square theta upon sine square 2 pi by 5. Now here the question is, resolve z to the power 5 plus 1 into linear and quadratic factors with real coefficients and then reduce that 4 sine pi by 10 into cos pi by 5 is equal to 1. Now we can write z to the power 5 plus 1 equals 0, then z is minus 1 to the power 1 by 5, which is minus 1 to the power 1 by 5. Now suppose alpha is fifth root of unity, which is e to the power iota 2 pi by 5, then 5 roots of z to the power 5 plus 1 are minus 1 minus alpha square minus alpha cube and minus alpha to the power 4. So we can write z to the power 5 plus 1 as z plus 1 z plus alpha square z plus alpha cube into z plus alpha to the power 4. Alpha to the power 4, which is 1 upon alpha, which we can write as alpha bar, and alpha cube is alpha bar square. So we'll replace alpha to the power 4 with alpha bar and alpha cube with alpha bar square. So we'll write this as z plus 1 into z plus alpha bar, z plus alpha square and z plus alpha bar square. Now we'll multiply these two factors and the other two factors. So we can write this as z plus 1 z square plus alpha bar z plus mod of alpha square and then z square plus alpha bar square z plus mod alpha to the power 4. Now mod of alpha is simply 1 and alpha plus alpha bar is 2 cos 2 pi by 5 and alpha square plus alpha bar square will be 2 cos 4 pi by 5. So we can write z to the power 5 plus 1 equals z plus 1 z square plus 2 cos 2 pi by 5 z plus 1 into z square plus 2 cos 4 pi by 5 z plus 1, and this is how we have factorized z to the power 5 plus 1 into linear and quadratic factors. Now using this, we need to deduce that this 4 sine pi by 10 into cos pi by 5 is equal to 1. We'll write cos 4 pi by 5 as cos pi minus pi by 5, and cos pi minus theta is minus cos theta. So it will be minus cos pi by 5. So we'll write z to the power 5 plus 1 as z plus 1 z square plus 2 cos 2 pi by 5z plus 1 into z square minus 2 cos pi by 5z plus 1. Now what we'll do is we'll let z equals 1. So we'll get 2 equals, and here this value will be 2. Here 1 plus 1 will be 2. We'll take this 2 common. We'll get 2 into 1 plus cos 2 pi by 5. And here also we'll take 2 common. We'll get 1 minus cos pi by 5. We'll cancel this 2 with 2. We can write 1 equals 4. 1 plus cos 2 pi by 5 into 1 minus cos pi by 5. Now we'll use half angle formula for both these factors. So we can write 1 equals 4, and this is 2 cos square pi by 5 into 2 sin square pi by 10. So from here we can say 4 cos pi by 5 into sin pi by 10, it is equal to 1. And this is what we need to prove. Now here the question is, if the expression z to the power 5 minus 32 can be factorized into linear and quadratic factors over real coefficients, then find the value of p square plus 2p. Now we know that if we have this polynomial equation z to the power 5 minus 32 equals 0, we can write this as z equals 32 to the power 1 by 5, which is 2 into 1 to the power 1 by 5. Now say alpha is e to the power iota 2 pi by 5, that is fifth root of unity. Then 5 roots of this equation are 2 alpha, 2 alpha square, 2 alpha cube, and 2 alpha to the power 4. Now since alpha is fifth root of unity, we know that alpha to the power 4 is alpha bar and alpha cube is alpha bar square. So 5 roots can also be expressed as 2 alpha, 2 alpha bar, 2 alpha square, and 2 alpha bar square. Now we can write z to the power 5 minus 32 as z minus 2, z minus 2 alpha, z minus 2 alpha bar, z minus 2 alpha square, and then z minus 2 alpha bar square. Now we'll multiply these two factors and these two factors. We can write z to the power 5 minus 32 will be z minus 2 z square minus 2 alpha plus alpha bar z plus 4, and here will be z square minus 2 alpha square plus alpha bar square z, and then plus 4. Now alpha plus alpha bar is 2 cos 2 pi by 5, and alpha square plus alpha bar square is 2 cos 4 pi by 5. So now we can write z to the power 5 minus 32 will be z minus 2 z square minus 4 cos 2 pi by 5 z plus 4 and z square minus 4 cos 4 pi by 5 plus 4. Now we compare, we'll get P as 4 cos 2 pi by 5. Which is 4 cos 72 degrees and which is also 4 sin 18 degrees. Now sin 18 degrees is root 5 minus 1 by 4. We'll cancel this 4 with 4. We can write P plus 1 equals root 5. Now we square it. We'll get P square plus 2P plus 1 LB5. From here we can say the value of P square plus 2P is nothing but 4. And that is the answer to this question. Now here the question is, resolve z to the power 7 minus 1 into linear and quadratic factors and hence deduce that cos pi by 7 into cos 2 pi by 7 into cos 4 pi by 7 is 1 by 8. Now say alpha is 7th root of unity, which is e to the power iota 2 pi by 7. Now we can write z to the power 7 minus 1 as z minus 1, z minus alpha square, z minus alpha cube, z minus alpha to the power 4, alpha to the power 5 and alpha to the power 6. Alpha to the power 6 is alpha bar, alpha to the power 5 is alpha bar square and alpha to the power 4 is alpha bar cube. So we can write this as z to the power 7 minus 1, z minus 1, z minus alpha bar, z minus alpha square, z minus alpha bar square and z minus alpha cube into z minus alpha bar cube. So we'll write this as z to the power 7 minus 1 will be z minus 1, z square minus alpha plus alpha bar z plus 1, z square minus alpha square plus alpha bar square z plus 1 and z square minus alpha cube plus alpha bar cube z plus 1, since alpha into alpha bar is 1. Now alpha plus alpha bar is 2 cos 2 pi by 7. This is 2 cos 4 pi by 7 and this is 2 cos 6 pi by 7. So we'll get this as z to the power 7 minus 1 will be z minus 1, z square minus 2 cos 2 pi by 7 z plus 1, z square minus 2 cos 4 pi by 7 z plus 1 and then z square. Now we can write cos 6 pi by 7 as cos pi minus pi by 7 and will be minus cos pi by 7. So it will be z square plus 2 cos pi by 7z plus 1. Now we need to find this product cos pi by 7 into cos 2 pi by 7 into cos. Now what we'll do is we'll put z as iota. So it will be iota to the power 7 minus 1 will be iota minus 1 and then we'll have minus 2 cos 2 pi by 7 iota minus 2 cos 4 pi by 7 iota and then 2 cos pi by 7 iota. Now this minus and minus will be plus Now iota to the power 7 is iota cube, which is minus iota. So we'll take minus common and we'll get this as 1 plus iota. Here it will be iota minus 1, and then 2 into 2 into 2 will be 8, and then iota cube. Iota cube is minus iota, and here we'll have cos pi by 7 into cos 2 pi by 7 into cos 4 pi by 7. Now we'll cancel this minus with minus. Now we multiply this iota here, we'll get iota square, which is minus 1 minus iota into 8, and it will be cos pi by 7 into cos 2 pi by 7 into cos 4 pi by 7. Now we take minus common. Here it will cancel, so we'll get this minus 1 here. So from here we can write the value of cos pi by 7 into cos 2 pi by 7 into cos 4 pi by 7. It is minus 1 by 8. So this result, cos pi by 7 into cos 2 pi by 7 into cos 4 pi by 7, it should be actually minus 1 by 8. Now the next question is, if alpha naught, alpha 1, alpha 2 and alpha n minus 1 are the roots nth roots of unity, then alpha k is cos 2 pi k by n plus iota sine 2 k pi by n. And we know that we can write x to the power n minus 1 as x minus alpha naught into x minus alpha 1 up to x minus alpha n minus 1. Now first question is, which is example 71, we need to find the value of 1 plus alpha naught, 1 plus alpha 1, 1 plus alpha n minus 1. And for that what we'll do is, we'll put x as minus 1. Now if we put x as minus 1, on the left hand side we'll get minus 1 to the power n minus 1 will be minus 1 minus alpha naught minus 1 minus alpha 1 up to minus 1 minus alpha to the power n minus 1. Now we'll take minus common from each of the bracket. Now if we take minus common from each of the bracket, we'll get minus 1 to the power n minus 1, and it'll be minus 1 to the power n 1 plus alpha naught into 1 plus alpha 1, 1 plus alpha n minus 1. Now we'll divide everything with minus 1 to the power n. Now we can write this as 1 plus alpha naught into 1 plus alpha 1, 1 plus alpha n minus 1 will be simply 1 plus minus 1 to the power n minus 1, and that's your option D. Now example 72 is, we need to find the value of 1 minus alpha 1 up to 1 minus alpha n minus 1. Now this is standard result. We know that 1 minus alpha 1, 1 minus alpha 2, 1 minus alpha n minus 1 is simply n, and that's your option A. We get this result by taking this limit x tends to 1, and here alpha naught is 1. So for 72, answer is A. Now we'll use this second result to prove this third result. Now the second result, we know that 1 minus alpha 1 into 1 minus alpha 2 up to 1 minus alpha to the power n minus 1, it is n. We can write this as this product k varies from 1 to n minus 1, and it will be 1 minus e to the power iota 2 pi k by n. Now what we'll do is, we'll take e to the power pi k by n common. So we can write k varies from 1 to n minus 1 e to the power iota pi k by n, and here will be e to the power minus iota pi k by n and minus e to the power iota pi k by n, and this value will be equal to n. Now this is cos theta minus iota sin theta minus cos theta plus iota sin theta. So it will be this product k varies from 1 to n minus 1 e to the power iota pi k by n, and here will be minus 2 iota sine pi k by n, and this value will be equal to n. Now we can write this as this product, which is 2 to the power n minus 1 sine pi by n sine 2 pi by n up to sine n minus 1 pi by n, which we need to find, and we'll say this expression is say E. This is E, and then into this product k varies from 1 to n minus 1, and then we are left with minus iota e to the power iota k pi by n. Now we can write iota as e to the power iota pi by 2. Now we can write this as e into, and then here will be minus iota minus iota minus iota n minus 1 times will be minus iota to the power n minus 1, and then we'll have e to the power iota pi by n, and it will be 1 plus 2 plus 3 up to n minus 1, and this value will be simply n. Now we can write this as e into minus iota to the power n minus 1, and here will be e to the power iota pi by n, and then n into n minus 1 by 2, and it is equal to n. This n and n will cancel, so we'll get this as e into minus iota to the power n minus 1, and then cos n minus 1 by 2 into pi plus iota sine n minus 1 by 2 into pi, and it is equal to n. Now we'll take 4 cases. Case 1, when n is of the form 4k. Now if n is of the form 4k, then we'll get this expression as e into minus iota to the power 4k minus 1, and here will be cos 4k minus 1 by 2, which is an odd multiple of pi by 2, so it will be 0, and plus iota sine 4k minus 1 into pi by 2, which is iota sine 2k pi minus pi by 2, and which is minus iota. We'll get this as e into minus iota to the power 4k will be equal to n, and minus iota to the power 4k is 1. So from here we'll get this value of e, it must be equal to n. Now we consider the second case when n is of the form 4k plus 1, then we'll get e into minus iota, and if we put n as 4k plus 1, we'll get minus iota to the power 4k into, now here it will be cos 2 pi plus iota sine 2 pi, which is 1, and it will be equal to n. Now again minus iota to the power 4k, it is 1. Again we'll get this result as this expression, it is equal to n. In the same way, we can prove it for n equals 4k plus 2n, n equals 4k plus 3. So in all the cases, we'll end up getting this result, which is e equals n. So we can say that value of this product, it is equal to n, and that's your option A. Now here the question is, if the equation z plus 1 to the power 7 plus z to the power 7 equals 0 has roots z1, z2 and z7, we need to find the value of summation r varies from 1 to 7 real zr and this summation imaginary zr. Now we can write this as z plus 1 to the power n will be equal to minus z to the power n. Now we can write this as z plus 1 upon z will be equal to minus 1 to the power 1 by n. Now nth root of unity is minus e to the power iota 2 pi r by n, where the value of r varies from 1 to 7. Now we can write this as 1 plus 1 upon z, it is equal to minus e to the power iota 2 pi r by n, z equals minus 1 upon 1 plus e to the power iota 2 pi r by n. Now what we'll do is we'll divide numerator and denominator with e to the power iota pi r by n. Then we can write this zr as minus e to the power minus iota pi r by n upon e to the power minus iota pi r by n plus e to the power iota pi r by n, which is minus cos pi r by n minus iota sine pi r by n upon 2 cos pi r by n. So we can write this zr as minus 1 by 2 plus 1 by 2 iota 10 pi r by n. Now we can write real part of zr is minus 1 by 2 and imaginary part of zr is 1 by 2 10 pi r by n. Then the first part we need to find this summation r varies from 1 to 7 real part of zr, which is nothing but this summation r varies from 1 to 7 minus 1 by 2, which is nothing but minus 7 by 2. And the second part we need to find this summation r varies from 1 to 7 imaginary part of zr will be this summation r varies from 1 to 7 1 by 2 10 pi r by n. Now we can write this as 1 by 2 10 pi by 7 plus 10 2 pi by 7 plus 10 3 pi by 7 plus 10 4 pi by 7 plus 10 5 pi by 7 plus 10 6 pi by 7 plus 10 7 pi by 7. Now 10 pi, it is 0. Now 6 pi by 7 is 10 pi minus pi by 7, which is minus 10 pi by 7. So it'll cancel. In the same way, 10 2 pi by 7 and 10 5 pi by 7 will cancel, and also 10 3 pi by 7 and 10 4 pi by 7 will cancel. So this summation of imaginary parts will be nothing but 0. So answer to this question is minus 7 by 2 for sum of real parts and 0 for the sum of imaginary parts. Find the roots of the equation z to the power n equals z plus 1 to the power n and show that the points which represent them are collinear on the complex plane. So we have already shown that roots of this equation are minus 1 by 2 iota cot pi r by n. Now real part of all these complex numbers is minus 1 by 2. So all these complex numbers, they will lie on this line, which is x equals minus 1 by 2, and therefore all these roots, they'll be collinear. So that's our first part. Now second part is, hence show that these roots are also the roots of the equation 2 sine m pi by n whole square z bar square plus 2 sine m pi by n whole square z bar plus 1 equals 0. Now what we'll do is, we'll take this equation and we'll write this as z plus 1 by 2 equals minus iota by 2 cot pi r by n, and if we take its conjugate, we'll get z bar, and here this value LB plus. Now we square both sides, we'll write z bar plus 1 by 2 square LB iota square, which is minus 1, so it'll be minus 1 by 4 cot square pi r square by n. Now we'll square this left hand side, we'll get mod of z square plus z bar plus 1 by 4, and here will be minus 1 by 4 cot square pi r by n. Now if we square this left hand side, we'll get z bar square plus z bar plus 1 by 4, and we'll take this also on the left hand side, we'll get 1 plus cot square pi r by n equals 0. Now 1 plus cot square theta is cosec square theta, so we'll write this as cosec square pi r by n, and if we write cosec square x as 1 upon sine square pi r by n, then we'll get z bar square plus z bar plus 1 by 4 sine square pi r by n, it is equal to 0. Now we'll multiply everything with 4 sine square pi r by n. So we'll write this as 2 sine pi r by n whole square into z bar square plus 2 sine pi r by n whole square into z bar plus 1 equals 0, which is same as the result that we need to prove. The only difference is they have used this integer as m. Now here the question is, it says, given that fx is x to the power 13 plus 2x to the power 12 plus 3x to the power 11 up to 14, and n is fa into fa square up to f e to the power 14, where a is 15th root of unity, then we need to find the value of m such that n to the power 1 by m is equal to 15. We'll write sum f e to the power r and LB e to the power 13r plus 2 into e to the power 12r, 3 into e to the power 11r up to 13 e to the power r plus 14, where this value of r varies from 1 to 14. Now again we'll write f e to the power r by displacing one term and dividing it with 1 upon e to the power r. So here we'll get e to the power 12r, 2 into e to the power 11r plus 13 and plus 14 upon e to the power r. Now we'll subtract this second series from first. We'll write 1 minus 1 upon e to the power r into f e to the power r will be equal to e to the power 13r, e to the power 12r up to 1 minus 14 upon e to the power r. Now what we'll also do is we'll add a to the power 14r and we'll subtract a to the power 14r. Now this is sum of rth power of 15th root of unity, and since this r, it doesn't divide 15, this sum will be simply 0. So from here we'll get a to the power r minus 1 upon a to the power r, f a to the power r will be equal to minus 14 plus a to the power 15r upon a to the power r. Now this a to the power r will cancel. Now a to the power 15, it is 1. So this f a to the power r will be simply minus 15 upon a to the power r minus 1, or 15 upon 1 minus a to the power r. Now we need to find the value of fa into fa square fa cube up to f a to the power 14 will be 15 into 15 into 15, 14 times, and there will be 15 to the power 14 upon 1 minus a square up to 1 minus a to the power 14. Now we know that 1 minus alpha square, 1 minus alpha to the power n minus 1 is nothing but n. So this value in the denominator will be nothing but 15. So this is 15 to the power 14 upon 15, and that is 15 to the power 13. Now in the question it says, if this n is 15 to the power 13, then we need to find the value of n such that n to the power 1 by m is 15. So we can write n to the power 1 by 13, it is 15. So value of m in this case will be 13, and that is the answer to this question. Now here the question is, let omega be 7th root of unity, and it says alpha is omega plus omega square plus omega to the power 4, and beta is omega cube plus omega to the power 5 plus omega to the power 6. Now the first question is we need to find the value of alpha plus beta. Now we know that alpha plus beta, it will be omega plus omega square plus omega cube plus omega to the power 4 plus omega to the power 5 plus omega to the power 6, which is sum of 7th root of unity except 1, and we know that this result is equal to minus 1. So this first result is value of alpha plus beta is minus 1, and that's your option B. Now second question is we need to find the value of alpha into beta. Now we multiply them, and the first one, if we take omega common, and from the second one we'll take omega cube common, we'll get omega into omega cube, and here we'll have 1 plus omega cube into 1 plus omega square plus omega cube. Now if we multiply them, we can write omega to the power 4, and here will be 1 plus omega cube plus omega square plus omega cube plus omega to the power 5 plus omega cube plus omega to the power 4 plus omega to the power 6. Now we know that 1 plus omega square plus omega cube plus omega 4 plus omega 5 plus omega to the power 6 is 0. So what we'll get is, we'll get alpha into beta equals omega to the power 4 into 2 omega cube. So we'll get alpha into beta is 2 omega to the power 7, and omega to the power 7 is 1. So we'll get alpha into beta is 2, and that's your option D. This third question is we need to find the equation whose roots are alpha and beta. Now we know that this quadratic equation will be x square minus sum x plus product equals 0. So it will be x square minus alpha plus beta, which is minus 1. So it will be x square plus x plus 2 equals 0, and that's your option B. Now the next part is we need to find the value of 2 alpha. Now alpha and beta, they are roots of this equation. So we'll get alpha and beta as -1 plus minus under root of 1 minus 8 upon 2. That means 2 alpha and 2 beta, it is given by -1 plus minus under root of 7 iota. Now what is alpha? Alpha is given as omega plus omega square plus omega to the power 4. So we know that alpha is omega plus omega square plus omega to the power 4. And if we look at imaginary part of alpha, it will be simply sine 2 pi by 7 plus sine 4 pi by 7 plus sine 8 pi by 7. Now 2 pi by 7, it is less than pi. 4 pi by 7 is also less than pi. And sine 8 pi by 7 is minus sine pi by 7, which is less than sine 2 pi by 7. So this value, it must be positive. So imaginary part of alpha, it must be greater than 0. So from here we can conclude that this 2 alpha, it must be -1 plus under root 7 iota, and that's your option A. Now question 85 is, we need to find this summation. K varies from 0 to 6 omega to the power k square. Now omega to the power 0 is 1, omega to the power 1 is omega, omega to the power 2 is omega to the power 4, omega to the power 9, omega to the power 16, omega to the power 25, and then omega to the power 36. Now this is 1 plus omega to the power 4. Now omega to the power 7 is 1, so it will be nothing but omega square. Now omega to the power 16 is omega square. Now omega to the power 25 is omega to the power 21 into omega to the power 4, so it will be omega to the power 4, and then omega to the power 36 is omega. So we can write this as 1 plus 2 omega plus omega square plus omega to the power 4, which is nothing but alpha. So it will be equal to 1 plus 2 alpha. And we know that value of 2 alpha is -1 plus root 7 iota. So 1 plus 2 alpha will be simply under root 7 iota, and that's your option B. Now here the question is, let n be an integer greater than 7 and let z to the power n minus 1 equals to 0 has roots 1, lambda 1, lambda 2 and lambda n minus 1. Then first question is, we need to find this summation lambda I. Now we know that sum of n roots of unity is 0. So we can write 1 plus lambda 1 plus lambda 2 plus lambda n minus 1 will be 0. Now we can write this as summation lambda I, where I varies from 1 to n minus 1. So it will be -1. So this option A, it is correct. Now this option D is product of all the roots. Now we know that product of all the roots is given by -1 to the power n, which is a standard result. So this D is also correct. Now from this option A, we can write lambda 1 plus lambda 2 up to lambda n minus 1. This value is -1. Now if we square it, we'll write lambda 1 square plus lambda 2 square plus lambda n minus 1 square plus 2 times, and then this summation lambda I, lambda j, and it will be equal to 1. Now we know that 1 square plus lambda 1 square plus lambda 2 square plus lambda n minus 1 square is also 0 since n doesn't divide 2. So we can write this as minus 1. So from here we can write 2 times this double summation lambda I into lambda j will be equal to 2. So this summation, it is equal to 1. That means this option B is also correct. Now we need to check this option C. Now we know that z to the power n minus 1 will be equal to z minus 1, and let us take this 1 as lambda naught. So we can write this as z minus lambda naught into z minus lambda 1, z minus lambda 2 up to z minus lambda n minus 1. Now if we find S3, and S3 is this triple summation lambda I into lambda j into lambda k, where I is greater than equal to 0 but less than j and less than k and less than equal to n minus 1, and S3 in this case will be simply 0. Now we can split this summation in 2 parts. First case, when I is equal to 0 and j is less than k is less than equal to n minus 1, lambda I, lambda j, lambda k, and then plus this summation 1 is less than equal to I, is less than j, is less than k, it is less than equal to n minus 1, lambda I into lambda j into lambda k, and this value it is 0. Now if we put I as 0, we'll get this as lambda naught, and lambda naught is 1. So we can write this as this double summation lambda j into lambda k plus this triple summation 1 is less than equal to I, is less than a, is less than k, is less than equal to n minus 1, lambda I, lambda j, lambda k, it is equal to 0. Now from this second result, we know that this is equal to 1. So from here we can write the value of this triple summation lambda I into lambda j into lambda k, where I is greater than 1 but less than j, less than k, less than equal to n minus 1 is minus 1. That means this option C is also correct. So for this question, all the 4 options are correct. Someone asked me this beautiful question in complex numbers, and the question is, let R1, R2, R3 up to R9 be the distinct complex roots of the polynomial Px x to the power 9 minus 9, and let k equals this product where I is greater than equal to 1 but less than j, which is less than equal to 9, ri plus rj, that is the product of all numbers of the form ri plus rj, where I and j are integers for which I is less than j and they lie between 1 and 9. We need to find the value of k square upon 9 to the power 7. Now we look at roots of this equation, which is x to the power 9 minus 9 equals to 0. We can write x to the power 9 as 9, and then I can write x as 9 to the power 1 by 9 into 1 to the power 1 by 9. Now we know that it is 9th root of unity. Now suppose the 9 roots of this equation are R1, R2, R3 and R9, and these 9 roots, they are of the form Rk can be expressed as 9 to the power 1 upon 9 e to the power iota 2 pi k by 9. Now we also know that we can express any polynomial as product of its factors. So we can write x to the power 9 minus 9 as x minus r1 into x minus r2, x minus r3 and up to x minus r9. Now in this equation, what we'll do is we'll put x as minus r1. So if I'll put x as minus r1, we'll write minus r1 to the power 9 minus 9, and this is minus 2r1 lb minus r1 minus r2 minus r1 minus r3 and minus r1 minus r9. So I can write it as minus. Now r1 to the power 9. Now since r1, r2 and rn, they are roots of this equation. So that means any rk to the power 9 will simply be 9. So we can write it as 9 plus 9, 18. So it will be minus 18. And here it will be, now this is minus, minus, minus from all the 9 factors. So there will be minus and then 2r1. And then it will be r1 plus r2. r1 plus r3 and then r1 plus r9. Now we'll put x as minus r2. Then again we'll get minus 18 and then here we'll get r1 plus r2, 2r2, r2 plus r3, r2 plus r9, and we'll keep doing it till r9, and then again we'll get minus 18 and here will be r9 plus r1, r9 plus r2, r9 plus r3, and then 2 times of r9. Now what we'll do is we'll multiply all these expressions. So we'll multiply all these expressions, we'll get 18 to the power 9, and then here will be 2 to the power 9 and then r1 into r2 into r9. So we'll get r1 into r2 up to r9 and then the product of all these numbers. Now if we look at this grid, of I and j, suppose here we have I and this is r1, r2, r3 and r9, and suppose here we have j, which is r1, r2 and r9. Now for the first one it will be 2r1, it will be r1 plus r2, r1 plus r3, r1 plus r9, and this is r2 plus r1, 2r2, r2 plus r9, and here will be r9 plus r1, r9 plus r2, and then 2 times of r9. So here we have these 9 products, which is 2r1, 2r2 and 2r9. So which we can write it as 2 to the power 9, r1 into r2 into r9. And then we have this product, which is r1 plus r2 and then r2 plus r1, r1 plus r3, and this is r3 plus r1. So that means here I'll get all the product, which is ri plus rj, where I is unequal to j. And since we have symmetry in the question, we can write this as 18 to the power 9 and this is 2 to the power 9 r1 into r2 into r9 into this product ri plus rj, where I is less than j whole square, because r1 plus r2 will be same as r2 plus r1. So that is the product of all the terms in this given matrix. So we can simply write it as 18 to the power 9 and this is 2 to the power 9. Now r1 into r2 into r9. So we can write it as product of all the terms. So r1, r2 into r9. So product of all the roots will be minus of minus, and then what is the equation? Equation is x to the power 9 minus 9. So this value, it should be 9. So here will be 9 and then this is nothing but k square. So we'll divide it with 2 to the power 9. We can write 9k square is equal to 9 to the power 9. So k square is 9 to the power 8. So we'll divide it with 9 to the power 7. We can write k square upon 9 to the power 7 is simply 9. So answer to this question is simply 9. Now here the question is, we are given a complex number w, which is root 3 plus iota upon 2, and we are given that this p is w to the power n. Now it says further h1 is all such z such that real part of z is greater than 1 by 2, and h2 is all such z where real part of z is less than minus 1 by 2, where c is set of all complex numbers. Now if z1 belongs to p intersection h1 and z2 belongs to p intersection h2, then we need to find angle between z1 o z2. Now if we look at this p is w to the power n, which is root 3 by 2 plus 1 by 2 iota to the power n, and this is e to the power iota pi by 6 to the power n. We can write this p as e to the power iota n pi by 6. Now we can also write this as e to the power iota 2n pi by 12. So basically this p is nothing but this is 12th root of unity. So this p is nothing but set of all 12th roots of unity. So now we have a circle. One of the root is 1, and then angle between any two successive roots will be 360 divided by 12, and that is 30 degrees. So we'll have these 12 roots of unity. So this is 1 alpha, alpha square, alpha cube, alpha to the power 4, alpha to the power 5, 6, 7, 8, 9, 10 and 11. Now we look at alpha square will be e to the power iota 4 pi by 12, which is pi by 3, and cos pi by 3 is 1 by 2, sin pi by 3 is root 3 by 2. So both these points, alpha square and alpha to the power 10, they will lie on x equals 1 by 2, and in the same way alpha to the power 4 and alpha to the power 8, they'll lie on x equals minus 1 by 2. Now z1 is p intersection h1, and h1 is when real part of z is greater than 1 by 2. So this z1, it could be either alpha 1 or alpha to the power 11, that is these three complex numbers, and z2 is p intersection h2, that is when real part is less than minus 1 by 2. So z2 could be these 3 points. Now what are the possible angles between z1 origin and z2? Now minimum angle will be 120 degrees. So it cannot be pi by 6. It cannot be pi by 2. Now this angle, it could be 2 pi by 3, which is 120, and it can also be 150. So the correct options are options C and D. Now here the question is, let V and W be distinct randomly chosen roots of the equation z to the power 1997 minus 1 equals 0, and let m by n be the probability that root of 2 plus root 3 is less than or equal to mod of v plus w, where m and n are relatively prime positive integers. Find m plus n. Now basically these are nth root of unity. Now one of the root is 1, and then we have alpha square. If we find angle between any two successive roots, and suppose that is theta, this angle is given by 360 divided by 1997. So that is the smallest possible unit of angle. Now we need to choose two roots v and w such that mod of v plus w is greater than or equal to root of 2 plus root 3. Now suppose we have two roots, say V and W, and angle between them is say alpha, then we can write mod of V plus W is greater than or equal to 2 plus root 3. Now we know that modulus of cube root of unity is 1. So this is 1 plus 1 plus 2 cos alpha, and will be greater than or equal to 2 plus root 3. Now 2 and 2 will cancel. So from here we'll get this condition that cos alpha is greater than or equal to root 3 by 2, or from here we can say value of alpha should lie between 0 and 30 degrees. Now suppose we choose any one root, then for this condition to be true, we have to choose the other root so that this angle is less than or equal to 30. Now we need to find how many choices do we have for such cases. So it will be this 0, and then n times theta should always be less than or equal to 30. Now this is 0 and this is n. Theta is 360 upon 1997 is less than or equal to 30. Now we simplify this. We'll get the value of n between 0 and 166.41. Now we cannot take 0 because then it will be the same root, and n has to be integer. So we can choose this other root in 166 ways for this to be true. Now this angle, it can be either clockwise or it can be in the anti-clockwise direction. So we have 166 other roots in other direction. So total number of favorable ways in which mod of u plus w will be greater than or equal to root of 2 plus root 3 is given by 332. So for any root, we have 332 favorable positions. So this required probability will be this 332 divided by, now how many total choices do we have? So there are 1997 roots, out of which 1 is V. So the remaining ones are 1996. So the required probability is 332 upon 1996, which is simply 83 by 499. And that is the answer to this question. Now here the question is, let A1, A2, A3 up to A8 be vertices of regular octagon lying on a circle of radius 2. Let P be point on a circle, and let PA1, PAI denote the distance between the points PAI for I equals 1 to 8. If P varies over the circle, then the maximum value of this product PA1, PA2 and PA8 is. Now basically what we'll do is, we'll draw a circle of radius 2 units and we're going to draw an octagon. So let this be O and radius is 2 units. And all these angles, they are simply 2 pi by 8, which is pi by 4. Now what we'll do is, here we're going to use nth root of unity, or basically 8th root of unity. So 8th root of unity there will be 1 alpha square and alpha to the power 7, but here in this case value of r is 2. So what we'll do is, we'll take roots as 2 alpha square and 2 alpha to the power 7. So without loss of generality, we'll arrange these numbers a1, a2, a3, a8 along these roots. So this is your a1, that's your a2, a3, a4, a5, a6, a7, and this is a8. So basically they are roots of this equation. z to the power 8 minus 2 to the power 8 equals 0, or we can write this as z to the power 8 minus 2 to the power 8 will be equal to z minus 2, z minus 2 alpha, z minus 2 alpha square up to z minus 2 alpha to the power 7. Now let us take any point P on this circle, and suppose this point is z0. So we can write z0 to the power 8 minus 2 to the power 8, and this is z0 minus 2, z0 minus 2 alpha up to z0 minus 2 alpha to the power 7. And if we take its mod, so we can write mod of z to the power 8 minus 2 to the power 8. It will be mod of z0 minus 2 into mod of z0 minus 2 alpha up to mod of z0 minus 2 alpha to the power 7. Now this is distance between two complex numbers. So this is basically PA1, this is PA2, and this is PA8. So we can write PA1 into PA2 up to PA8, and that will be equal to z to the power 8 minus 2 to the power 8. Now since this P, it lies on this circle, so we can write this z0 as sum 2 e to the power iota theta. So it will be 2 to the power 8 plus e to the power iota 8 theta minus 2 to the power 8. Now we'll take 2 to the power 8 common. So it will be this 2 to the power 8 e to the power iota 8 theta minus 1. Now what we'll do is we'll try and find the maximum value of this expression on the right hand side, so that we'll get the maximum value of this expression on the left hand side. Now here what we'll do is we'll take e to the power iota 4 theta common, so we can write 2 to the power 8 mod of e to the power iota 4 theta, and here will be e to the power iota 4 theta minus e to the power minus iota 4 theta. Now we know that mod of z1 into z2 is mod of z1 into mod of z2. So we can write this as 2 to the power 8 mod of e to the power iota 4 theta into mod of e to the power iota 4 theta minus e to the power minus iota 4 theta. Now this is cos theta plus iota sin theta minus cos theta minus iota sin theta. Here cos theta will cancel. So we can write 2 to the power 8, and here modulus is 1, so it will be this 1, and here will be 2 iota sine 4 theta. Now mod of iota is 1, so we can write this as 2 to the power 9 sine 4 theta. Now maximum value of sine is 1, so it will always be less than 2 to the power 9, which is 512. So the maximum value of this product PA1, PA2, PA8 is 512. So the maximum value of this product PA1 into PA2 up to PA8 will be 512, and that is the answer to this question.